What if I told you that the universe has its own way of bending reality, creating cosmic mirages that defy our understanding of space and time? Imagine looking through a telescope and seeing the same galaxy not once, but multiple times, stretched and warped into a surreal cosmic tapestry. This isn't science fiction, it's gravitational lensing, one of the most extreme and mind-bending phenomena in the universe. Gravitational lensing occurs when massive objects, like galaxies or black holes, warp the fabric of spacetime so profoundly that they bend the light traveling from distant objects behind them. It's like nature's magnifying glass, allowing us to peer deeper into the cosmos than ever before. But it's not just a cosmic curiosity. Gravitational lensing is a powerful tool that helps us unravel the mysteries of dark matter, map the universe's hidden structures, and even glimpse the earliest moments after the Big Bang. In this video, we're diving into 50 astonishing facts about gravitational lensing, from its mind-blowing effects to its role in shaping our understanding of the universe. By the end, you'll see the cosmos in a whole new light, literally. So, are you ready to explore the universe's most extreme gravitational lenses? Let's begin. Now, let's start with the basics. What exactly is gravitational lensing? Picture this: you're holding a magnifying glass over a piece of paper, and as you move it, the light passing through bends and distorts the image beneath. Gravitational lensing works in a similar way, but instead of a magnifying glass, it's the immense gravity of massive objects like galaxies or black holes that does the bending. These cosmic heavyweights warp the fabric of spacetime itself, causing light from distant objects behind them to curve around them. This bending of light can create some truly bizarre and beautiful effects. For example, a single distant galaxy might appear as multiple images, stretched and twisted into arcs or rings. It's like looking at a funhouse mirror where the reflection is distorted but still recognizable. The key here is mass. The more massive the object, the stronger its gravitational pull, and the more dramatic the lensing effect. But gravitational lensing isn't just a cosmic optical illusion. It's a powerful tool that allows astronomers to see objects that would otherwise be too faint or far away to detect. By studying how light bends around these massive objects, scientists can uncover hidden details about the universe, from the distribution of dark matter to the properties of distant galaxies. So, in a way, gravitational lensing is like nature's ultimate telescope, giving us a front-row seat to the most extreme corners of the cosmos. Now, let's take a step back in time to explore how this incredible phenomenon was first predicted. In the early 20th century, Albert Einstein revolutionized our understanding of gravity with his theory of general relativity. One of the most fascinating predictions to emerge from this theory was the idea that massive objects could bend light. Einstein proposed that objects like stars or galaxies, with their immense gravitational pull, could warp the fabric of spacetime so profoundly that light traveling near them would curve. This groundbreaking idea was the first scientific prediction of what we now call gravitational lensing. At the time, Einstein's prediction was met with skepticism. After all, the idea that something as intangible as gravity could bend light seemed almost too extraordinary to believe. But Einstein's equations were clear: massive objects would distort spacetime, and light would follow that curvature. It wasn't until decades later, in the 1970s, that astronomers finally observed this phenomenon in action. The first confirmed instance of gravitational lensing came with the discovery of the twin quasar, a distant object whose light was split into multiple images by a massive galaxy in between. This discovery not only validated Einstein's prediction, but also opened up a whole new way for scientists to study the universe. The significance of Einstein's prediction can't be overstated. It wasn't just a theoretical curiosity, it was a profound insight into the nature of gravity and light. By confirming gravitational lensing, astronomers gained a powerful tool to explore the cosmos. It allowed them to measure the mass of distant galaxies, map the distribution of dark matter, and even test the very foundations of general relativity. Einstein's vision of a universe where gravity bends light has become one of the cornerstones of modern astrophysics, proving once again that sometimes the most extraordinary ideas are the ones that change everything. With this foundation in place, let's move forward to explore how gravitational lensing works in even greater detail, uncovering the science behind this cosmic phenomenon. Now, let's dive into the story of the first gravitational lens ever observed, a discovery that changed the way we see the universe. In the year 1979, astronomers made a groundbreaking observation. A distant quasar known as QSO 0957+561 appeared not once but twice in the night sky. This peculiar double image was the result of a massive galaxy sitting directly between the quasar and Earth, bending its light and creating what we now call the twin quasar. This discovery was nothing short of revolutionary. For the first time, scientists had direct evidence that Einstein's prediction of gravitational lensing was not just a theoretical idea, it was a real, observable phenomenon. The twin quasar became a cosmic laboratory, allowing astronomers to test and refine their understanding of gravity, light, and the structure of the universe. By studying the way the quasar's light was split and distorted, researchers could measure the mass of the intervening galaxy with unprecedented precision. But the implications went even further. The twin quasar opened the door to a whole new way of exploring the cosmos. Suddenly, astronomers realized they could use gravitational lensing as a natural telescope, magnifying distant objects that would otherwise be too faint or too far away to see. This technique allowed them to peer deeper into space and further back in time than ever before, uncovering galaxies and quasars from the early universe. The twin quasar also provided crucial insights into the nature of dark matter. By analyzing how the lensing effect distorted the quasar's light, scientists could map the distribution of dark matter in the intervening galaxy, offering a glimpse into the invisible scaffolding that holds the universe together. This discovery marked the beginning of a new era in astrophysics, where gravitational lensing became one of the most powerful tools for studying the cosmos. As we continue our journey through the universe's most extreme gravitational lensing events, the twin quasar stands as a testament to the power of curiosity and the enduring legacy of Einstein's vision. It reminds us that sometimes the most profound discoveries come from seeing the universe in a whole new light. Next, we'll explore the science behind how gravitational lensing works, breaking down the mechanics of this incredible cosmic phenomenon. Now, let's take a closer look at the fascinating mechanics behind gravitational lensing. At its core, this phenomenon is all about the interplay between mass, spacetime, and light. Imagine spacetime as a vast, flexible fabric. When a massive object, like a galaxy or a black hole, sits on this fabric, it creates a deep curve or dent. This curvature is what we call spacetime bending, and it's the key to understanding how gravitational lensing works. When light from a distant object, such as a quasar or a galaxy, travels through this curved spacetime, it doesn't move in a straight line. Instead, it follows the curve created by the massive object's gravity. Think of it like rolling a marble across a bent sheet. It doesn't go straight, it follows the dip. This bending of light is what causes the distant object to appear distorted, magnified, or even multiplied in our telescopes. The amount of bending depends on two main factors: the mass of the object causing the lensing and the alignment between the distant object, the lensing object, and the observer. The more massive the lensing object, the stronger the curvature of spacetime, and the more dramatic the lensing effect. This is why galaxy clusters, which contain enormous amounts of mass, are some of the most powerful gravitational lenses in the universe. But it's not just about mass, it's also about the path the light takes. If the alignment is just right, the light can take multiple paths around the lensing object, creating multiple images of the same background object. This is what we saw with the twin quasar, where the light from a single quasar was split into two distinct images by a massive galaxy in between. Gravitational lensing also has a magnifying effect. Just like a magnifying glass can make small objects appear larger, the curvature of spacetime can amplify the light from distant objects, making them appear brighter and more detailed than they would otherwise. This natural magnification allows astronomers to study objects that would be too faint or too far away to observe directly. To sum it up, gravitational lensing is a cosmic dance of mass, light, and spacetime. It's a powerful reminder of how the universe bends the rules of physics in the most extraordinary ways. Next, we'll explore the different types of gravitational lensing and how each one reveals unique insights about the cosmos. Now that we've explored how gravitational lensing works, let's dive into the different flavors of this cosmic phenomenon. Gravitational lensing comes in three main types, each with its own unique characteristics and applications in astronomy. These are strong lensing, weak lensing, and microlensing. Each type reveals different aspects of the universe, from the structure of galaxy clusters to the discovery of distant planets. First up is strong lensing, the most dramatic and visually striking form of gravitational lensing. This occurs when a massive object, like a galaxy cluster, creates such a deep curve in spacetime that it produces highly distorted, magnified, or even multiple images of a background object. A classic example of strong lensing is the Einstein ring, where a distant galaxy appears as a perfect ring around the lensing object due to precise alignment. Another famous example is the twin quasar, where a single quasar is split into two distinct images by a massive galaxy in between. Strong lensing is like the universe's way of giving us a magnifying glass to study distant galaxies and quasars in incredible detail. Next, we have weak lensing, which is more subtle but no less important. Weak lensing occurs when the distortion of background objects is slight, often just a small stretching or warping of their shapes. This type of lensing is typically caused by less massive objects or those that aren't perfectly aligned with the observer. While the effects are less dramatic, weak lensing is incredibly useful for mapping the distribution of dark matter in the universe. By studying how the shapes of millions of distant galaxies are subtly distorted, astronomers can create detailed maps of the invisible dark matter that shapes the cosmos. It's like using a soft touch to uncover the hidden scaffolding of the universe. Finally, there's microlensing, which involves smaller objects like individual stars or even planets. In microlensing, a foreground object passes in front of a distant star, temporarily magnifying its light. This effect is brief but powerful, often lasting days or weeks. Microlensing has been instrumental in discovering exoplanets, especially those that are too faint or distant to detect by other methods. For example, microlensing has revealed rogue planets' worlds that wander through space without orbiting a star. It's like catching a fleeting glimpse of something extraordinary, a momentary flash of insight into the vastness of the cosmos. Each type of gravitational lensing offers a unique window into the universe, from the grand distortions of strong lensing to the delicate hints of weak lensing and the fleeting magnifications of microlensing. Together, they help astronomers piece together the intricate puzzle of our cosmos, revealing everything from the nature of dark matter to the existence of distant worlds. Up next, we'll take a closer look at strong lensing and some of the most breathtaking examples it has to offer. Now that we've covered the basics of gravitational lensing and its three main types, let's zoom in on strong lensing, the most visually stunning and dramatic form of this cosmic phenomenon. Strong lensing happens when a massive object, like a galaxy cluster, bends spacetime so intensely that it creates striking distortions of background objects. These distortions can take the form of multiple images, arcs, or even complete rings of light. offering astronomers a front-row seat to some of the most extreme and beautiful events in the universe. One of the most iconic examples of strong lensing is the Einstein ring. Named after Albert Einstein, who first predicted this effect, an Einstein ring occurs when a distant object, like a galaxy or quasar, is perfectly aligned behind a massive lensing object. The result is a breathtaking ring of light encircling the foreground object. A famous example is the cosmic horseshoe, a nearly perfect Einstein ring discovered in 2005. This ring, formed by a distant galaxy magnified by a foreground galaxy cluster, is one of the largest and most complete Einstein rings ever observed. It's like the universe's way of creating a cosmic halo, giving us a rare and mesmerizing glimpse into the distant cosmos. Another remarkable example of strong lensing is the twin quasar, also known as QSO 0957+561. Discovered in 1979, this was the first gravitational lens ever observed. Here, a single quasar appears as two distinct images due to the gravitational influence of a massive galaxy positioned between the quasar and Earth. This discovery not only confirmed Einstein's predictions, but also opened up a whole new way of studying the universe. By analyzing the light from these multiple images, astronomers can measure the expansion rate of the universe and even study the properties of the lensing galaxy itself. Strong lensing also plays a crucial role in studying some of the most distant objects in the universe. For instance, the galaxy cluster Able 1689, located about 2.3 billion light-years away, acts as a powerful cosmic magnifying glass. Its immense mass distorts and magnifies the light from galaxies even farther behind it, allowing astronomers to observe galaxies that would otherwise be too faint to detect. This cluster has revealed some of the earliest galaxies ever seen, giving us a glimpse into the universe's infancy. But strong lensing isn't just about beauty and discovery. It's also a powerful tool for probing the mysteries of dark matter. By studying how light bends around massive objects, scientists can map the distribution of dark matter within galaxy clusters. This invisible substance, which makes up most of the universe's mass, doesn't emit light, but its gravitational effects are clearly visible through strong lensing. It's like using the universe's own distortions to uncover its deepest secrets. From Einstein rings to multiple images of distant quasars, strong lensing offers a window into the most extreme and fascinating corners of the cosmos. Up next, we'll explore how weak lensing, though less dramatic, plays an equally important role in unraveling the universe's mysteries. Now, let's shift our focus to a more subtle but equally fascinating aspect of gravitational lensing, weak lensing. Unlike the dramatic distortions of strong lensing, weak lensing involves much gentler effects, subtly altering the shapes of distant galaxies. These changes are so slight that they're often invisible to the naked eye, but with the help of advanced telescopes and sophisticated data analysis, astronomers can detect and measure them. Weak lensing occurs when the gravitational influence of a massive object, like a galaxy cluster or even a large concentration of dark matter, slightly bends the light from background galaxies. Instead of creating multiple images or rings, weak lensing stretches and distorts the shapes of these galaxies, making them appear slightly elongated or aligned in a particular direction. Imagine looking at a field of distant galaxies through a slightly warped window. Their shapes are subtly changed, but not enough to completely transform them. This subtle effect is incredibly powerful for mapping the distribution of dark matter across the universe. Since dark matter doesn't emit or absorb light, it's invisible to traditional telescopes. However, its gravitational pull affects the light from background galaxies, creating the weak lensing distortions we observe. By studying these distortions, scientists can create detailed maps of dark matter, revealing its presence and distribution on a cosmic scale. It's like using the universe's own light as a tool to uncover its hidden structure. Weak lensing also plays a crucial role in understanding the large-scale structure of the universe. On the grandest scales, galaxies and galaxy clusters are not randomly scattered. They form a vast cosmic web connected by filaments of dark matter. Weak lensing helps astronomers trace this web, providing insights into how the universe evolved over billions of years. By analyzing the patterns of distortion in millions of galaxies, researchers can piece together the history of cosmic expansion and the role of dark energy in shaping the universe. One of the most ambitious projects to study weak lensing is the Dark Energy Survey, which has mapped the shapes of hundreds of millions of galaxies across a large portion of the sky. This massive dataset has provided unprecedented insights into the distribution of dark matter and the nature of dark energy, the mysterious force driving the accelerated expansion of the universe. Weak lensing, though less flashy than its strong counterpart, is a cornerstone of modern cosmology, helping us unravel the universe's deepest mysteries. As we continue our journey through the wonders of gravitational lensing, let's turn our attention to microlensing, where smaller objects like stars or planets create temporary magnifications of background objects, opening up new possibilities for discovery. Now let's zoom in on a fascinating and slightly different form of gravitational lensing, microlensing. While strong and weak lensing involve massive objects like galaxies or galaxy clusters, microlensing focuses on smaller cosmic players such as stars, planets, or even black holes. These smaller objects can still bend light, but their effects are more subtle and temporary. When a smaller object passes directly between us and a distant star, it acts like a cosmic magnifying glass, briefly amplifying the star's light. This temporary brightening can last anywhere from hours to days, depending on the alignment and the mass of the lensing object. What makes microlensing so exciting is its ability to reveal objects that are otherwise invisible to us. For example, microlensing has been a game changer in the search for exoplanets, planets orbiting stars outside our solar system. When a star with an orbiting planet passes in front of a more distant star, the planet's gravity can create a secondary magnification effect, revealing its presence. This technique has allowed astronomers to discover exoplanets that are too distant, too faint, or too small to be detected by other methods. It's like finding a needle in a cosmic haystack, but with the universe itself providing the magnifying glass. But microlensing doesn't stop at exoplanets. It has also uncovered a population of rogue planets, worlds that don't orbit any star at all. These free-floating planets wander through the galaxy, untethered to a solar system, and are nearly impossible to detect without microlensing. When one of these rogue planets passes in front of a distant star, it creates a brief but detectable spike in brightness, giving astronomers a rare glimpse into these mysterious solitary worlds. Some of these rogue planets may have been ejected from their original solar systems, while others might have formed on their own in the cold depths of space. Either way, microlensing has opened a window into a previously hidden corner of the cosmos. One of the most famous microlensing discoveries is the exoplanet Hubble 2013 BLG 0321, located an astonishing 13,000 light-years away. This planet, roughly the size of Jupiter, was detected through a microlensing event that lasted just a few weeks. Without microlensing, such a distant world would have remained invisible to us. Similarly, microlensing has helped identify rogue planets like MOA 2011 BLG 262, a small, Earth-sized world drifting alone through the galaxy. Microlensing is not just a tool for discovery, it's also a way to study the distribution of objects in our galaxy. By analyzing the frequency and characteristics of microlensing events, astronomers can estimate how many stars, planets, and rogue worlds populate the Milky Way. This data helps us understand the structure and evolution of our galaxy, painting a more complete picture of the cosmic neighborhood we call home. As we continue to explore the universe's most extreme gravitational lensing phenomena, let's turn our attention to another breathtaking effect: Einstein rings, where the alignment of a lensing object and a distant star creates a perfect ring of light. Now, let's step into the mesmerizing world of Einstein rings, one of the most striking visual effects created by gravitational lensing. Imagine a distant star or galaxy perfectly aligned behind a massive object, like a galaxy cluster or a black hole. The immense gravity of the foreground object bends the light from the background source, warping it into a stunning, circular ring of light. This phenomenon, predicted by Albert Einstein himself, is what we call an Einstein ring. It's like nature's way of drawing a glowing halo in the cosmos, a cosmic bullseye that captures the imagination. Einstein rings occur when the alignment between the lensing object, the distant light source, and the observer is just right. The light from the background object gets bent around the massive foreground object in such a way that it forms a complete circle. These rings are not just beautiful, they're also incredibly useful for astronomers. By studying the shape and size of an Einstein ring, scientists can measure the mass of the lensing object and even map the distribution of dark matter within it. It's like using the universe's own magnifying glass to peer into the invisible. One of the most famous examples of an Einstein ring is the cosmic horseshoe, a breathtaking ring of light discovered in 2007. This ring is formed by a distant galaxy, located nearly 5 billion light-years away, being lensed by a massive foreground galaxy. The result is a near-perfect circle of light, glowing like a celestial jewel in the depths of space. The cosmic horseshoe is not just a visual marvel, it's also a treasure trove of information, helping astronomers understand the properties of both the lensing galaxy and the distant one behind it. Another stunning example is the galaxy SDSS-J0946+1006, which creates a double Einstein ring. In this rare case, two distant galaxies are perfectly aligned behind a massive foreground galaxy, producing not one but two concentric rings of light. It's like a cosmic ripple effect, a snapshot of gravity's artistry on a grand scale. These double rings are incredibly rare, offering a unique opportunity to study multiple galaxies at once and probe the structure of the universe itself. Einstein rings are more than just a cosmic curiosity. They're a powerful tool for exploring the universe. They allow us to see objects that would otherwise be too faint or too distant to observe, acting as natural telescopes that amplify the light from the far reaches of space. By studying these rings, astronomers can uncover the secrets of dark matter, measure the expansion rate of the universe, and even test the predictions of Einstein's theory of general relativity. As we marvel at these glowing rings of light, let's turn our attention to another incredible achievement in the study of gravitational lensing: the role of the Hubble Space Telescope in capturing some of the most iconic images of this phenomenon. Now, shifting our gaze to the stars, let's explore the incredible contributions of the Hubble Space Telescope in unraveling the mysteries of gravitational lensing. Since its launch in 1990, Hubble has been a game-changer for astronomy, capturing some of the most breathtaking and scientifically valuable images of the cosmos. Among its many achievements, Hubble has played a pivotal role in observing and studying gravitational lensing, giving us a front-row seat to this extraordinary phenomenon. Hubble's sharp vision and ability to peer deep into space have allowed it to capture stunning examples of gravitational lensing, from Einstein rings to multiple images of distant galaxies. One of its most iconic contributions is the Hubble Deep Field, an image that revealed thousands of galaxies, many of which were magnified and distorted by gravitational lensing. This single image transformed our understanding of the universe, showing just how powerful lensing can be in revealing the hidden depths of space. But Hubble's role goes beyond just taking pretty pictures. Its observations have provided critical data for scientists studying the distribution of dark matter, the expansion of the universe, and the properties of distant galaxies. For instance, Hubble's images of galaxy clusters like Able 1689 have allowed astronomers to map the invisible dark matter within these clusters by analyzing how they bend the light from background objects. It's like using a cosmic magnifying glass to see the unseen. Hubble has also been instrumental in discovering some of the most extreme gravitational lensing events. Take, for example, the galaxy cluster MAX J0717.5 plus 3745, one of the most massive and complex lensing systems ever observed. Hubble's images of this cluster revealed multiple arcs and distorted galaxies, providing a treasure trove of information about the cluster's mass and structure. These observations have helped scientists test and refine our understanding of gravity and the large-scale structure of the universe. Perhaps one of Hubble's most remarkable achievements in gravitational lensing is its role in the Hubble Frontier Fields project. This ambitious initiative combined Hubble's observations with the natural magnification of massive galaxy clusters to peer deeper into the universe than ever before. By using these clusters as natural telescopes, Hubble revealed galaxies from the early universe, some of which existed just a few 100 million years after the Big Bang. These discoveries have given us unprecedented insights into the formation and evolution of galaxies. Hubble's legacy in the study of gravitational lensing is undeniable. Its images have not only expanded our knowledge of the universe, but also inspired awe and wonder in people around the world. As we continue to explore the cosmos, Hubble's contributions remind us of the power of observation and the beauty of discovery. And with that, let's turn our attention to another fascinating aspect of gravitational lensing, its role in helping us understand the elusive nature of dark matter. Now, let's dive into one of the most intriguing connections in modern astrophysics: gravitational lensing, and its role in uncovering the secrets of dark matter. Dark matter, an invisible and mysterious substance, makes up about 85% of the universe's total mass. Yet, because it doesn't emit, absorb, or reflect light, it's incredibly difficult to detect directly. This is where gravitational lensing becomes a game changer. When light from distant galaxies passes through regions of space filled with dark matter, the immense gravitational pull of this invisible substance bends the light, creating distortions in the images we observe. By studying these distortions, scientists can map the distribution of dark matter, even though we can't see it directly. It's like using the bending of light as a cosmic detective tool to reveal the hidden structure of the universe. One of the most famous examples of this is the Bullet Cluster, a collision between two galaxy clusters. Observations of this event showed that the visible matter, like gas and stars, behaved differently from the dark matter. The gas slowed down due to friction, while the dark matter continued moving, unaffected. Gravitational lensing revealed the separation between the two, providing some of the strongest evidence yet for the existence of dark matter. But dark matter isn't just a passive player in the cosmos. It plays a crucial role in shaping the universe on the largest scales. Without dark matter, galaxies wouldn't have enough gravitational pull to hold themselves together, and the large-scale structure of the universe, filaments, voids, and clusters, wouldn't exist as we know it. Gravitational lensing allows us to study how dark matter influences the formation and evolution of these cosmic structures, giving us a deeper understanding of the universe's architecture. In essence, gravitational lensing acts as a bridge between the visible and the invisible, helping us piece together the puzzle of dark matter. By analyzing how light bends around massive objects, scientists can infer the presence and distribution of dark matter, shedding light on one of the greatest mysteries in modern science. And as we continue to explore, gravitational lensing will undoubtedly remain one of our most powerful tools in unraveling the secrets of the cosmos. Next, let's explore how this phenomenon has helped us observe some of the most distant objects in the universe. Now, let's take a closer look at one of the most groundbreaking discoveries in the study of dark matter: the Bullet Cluster. This remarkable cosmic event is not just a collision between two galaxy clusters. It's a cosmic detective story that revealed the invisible hand of dark matter in shaping the universe. The Bullet Cluster, officially known as one galaxy cluster passing through another, offers a rare and stunning glimpse into the interplay between visible matter and its elusive counterpart. When these two galaxy clusters collided, something extraordinary happened. The hot gas within the clusters, which makes up most of the visible matter, slowed down due to friction, creating a shock wave that resembles a bullet piercing through space, hence the name. But here's where it gets fascinating. While the gas slowed, the dark matter within the clusters kept moving, unaffected by the collision. This separation between the visible gas and the dark matter was captured using gravitational lensing, which revealed the distribution of dark matter through the bending of light from background galaxies. The images of the Bullet Cluster are nothing short of breathtaking. The visible gas, glowing in X-rays, appears as a bright, distorted cloud, while the dark matter, mapped through gravitational lensing, forms two distinct clumps that passed right through each other. This separation provided some of the most compelling evidence for the existence of dark matter, as it demonstrated that dark matter interacts differently from ordinary matter, gravitationally but not electromagnetically. What makes the Bullet Cluster so significant is that it didn't just confirm the presence of dark matter, it also showed how dark matter behaves on cosmic scales. Unlike ordinary matter, dark matter doesn't collide or slow down in the same way, allowing it to dominate the gravitational landscape of the universe. This discovery was a turning point in astrophysics, solidifying dark matter as a fundamental component of the cosmos. The Bullet Cluster also highlights the power of gravitational lensing as a tool for uncovering the unseen. By analyzing how light from distant galaxies was bent around the cluster, scientists could map the dark matter's distribution with incredible precision. This technique has since been used to study other galaxy clusters, further confirming the role of dark matter in shaping the universe. In many ways, the Bullet Cluster is a cosmic Rosetta Stone, helping us decode the mysteries of dark matter and its influence on the universe's structure. It's a testament to how gravitational lensing allows us to see the invisible, turning the bending of light into a window into the hidden workings of the cosmos. Next, we'll explore how gravitational lensing has allowed us to observe some of the most distant objects in the universe, acting as a natural telescope to peer into the depths of space and time. Now, let's shift our focus to another fascinating aspect of gravitational lensing: time delays. This phenomenon occurs when light from a single distant object, like a quasar or galaxy, takes multiple paths around a massive lensing object, such as a galaxy cluster or black hole. Because these paths vary in length and the gravitational pull affects the speed of light differently along each path, the light doesn't arrive at Earth all at once. Instead, it reaches us at different times, creating what scientists call a time delay. Imagine a cosmic traffic jam where light rays are like cars taking different routes to the same destination. Some routes are longer or more congested, causing delays. In the case of gravitational lensing, the congestion is caused by the curvature of spacetime around the massive lensing object. This means that even though the light originates from the same source, we see multiple images of that source appearing at slightly different times. These time delays can range from days to years, depending on the mass of the lensing object and the alignment of the system. One of the most famous examples of this is the quasar known as SDSS-J 1004+4112. This quasar appears as four distinct images due to the gravitational lensing effect of a massive galaxy cluster. The light from each image takes a different path, resulting in time delays of several weeks between the images. By studying these delays, astronomers can measure the expansion rate of the universe, a key parameter in cosmology known as the Hubble constant. This helps us understand how fast the universe is expanding and provides insights into the nature of dark energy, the mysterious force driving this acceleration. Time delays in gravitational lensing also offer a unique way to study the distribution of mass within the lensing object itself. By analyzing how the light bends and the delays between images, scientists can map the mass of the lensing galaxy or cluster with incredible precision. This has led to discoveries about the structure of dark matter halos and how they influence the bending of light, but the implications go even further. Time delays can also help us test Einstein's theory of general relativity on cosmic scales. By comparing the observed delays with predictions from the theory, scientists can confirm whether our understanding of gravity holds true in extreme environments. So far, the results have consistently supported Einstein's predictions, but future observations could reveal new insights or even hints of new physics. In essence, time delays in gravitational lensing are like cosmic stopwatches, allowing us to measure the universe in ways that would otherwise be impossible. They provide a unique window into the structure of spacetime, the distribution of mass, and the expansion of the cosmos. Next, we'll explore how gravitational lensing has allowed us to observe some of the most distant objects in the universe, acting as a natural telescope to peer into the depths of space and time. Now, let's journey even deeper into the cosmos, where gravitational lensing becomes our ultimate tool for exploration. One of the most extraordinary capabilities of this phenomenon is its ability to act as a natural telescope, magnifying the light from some of the most distant objects in the universe. These objects, like ancient galaxies and quasars, are so far away that their light has traveled for billions of years to reach us. Without gravitational lensing, they would remain invisible, lost in the vast expanse of space. Imagine looking through a cosmic magnifying glass that not only brings distant objects into view, but also reveals details that would otherwise be impossible to see. This is exactly what gravitational lensing does. When a massive object like a galaxy cluster lies between us and a distant galaxy or quasar, it bends and amplifies the light from that object, making it appear brighter and larger. This magnification allows astronomers to study these ancient objects in unprecedented detail, offering a glimpse into the early universe. One of the most remarkable examples of this is the galaxy known as MAX 1149+2223, which holds the record for one of the most distant galaxies ever observed. Thanks to the gravitational lensing effect of a massive galaxy cluster, this galaxy appears magnified, allowing scientists to study its properties and learn about the conditions of the universe when it was just a fraction of its current age. Similarly, quasars, the incredibly bright cores of distant galaxies powered by supermassive black holes, have been observed through lensing, revealing details about the early stages of galaxy formation and the evolution of the cosmos. But why is this so important? Observing these distant objects helps us piece together the history of the universe. They act as cosmic time capsules, preserving information about the universe's infancy. By studying their light, we can learn about the first generations of stars, the formation of galaxies, and the conditions that existed shortly after the Big Bang. Gravitational lensing, in this sense, is like a time machine, allowing us to peer back into the universe's past. Moreover, these observations provide critical insights into the nature of dark matter and dark energy. The way light bends around massive objects depends on the distribution of dark matter, and studying these distant lensed objects helps us map this invisible substance. At the same time, the brightness and distance of these objects give us clues about the rate of the universe's expansion, shedding light on the mysterious force of dark energy. In essence, gravitational lensing doesn't just magnify distant objects, it magnifies our understanding of the universe. By acting as a natural telescope, it allows us to explore the farthest reaches of space and time, uncovering secrets that would otherwise remain hidden. Next, we'll dive into how this cosmic magnifying glass works in even greater detail, revealing how it magnifies distant objects and helps us study the early universe. Now, let's take a closer look at how gravitational lensing acts as a cosmic magnifying glass, bringing the faintest and most distant objects into sharp focus. When light from a distant galaxy or quasar passes near a massive object like a galaxy cluster, the immense gravity of that object bends the light, much like a magnifying glass bends light to make objects appear larger. This bending not only distorts the image but also amplifies the light, making the distant object appear brighter and more detailed than it would otherwise. This magnification is incredibly powerful. In some cases, gravitational lensing can make a distant object appear up to 50 times brighter than it would without the lensing effect. This is a game changer for astronomers, as it allows them to study objects that would otherwise be too faint or too small to detect with even the most advanced telescopes. For example, without gravitational lensing, many of the earliest galaxies in the universe would remain hidden, their light too dim to reach us across billions of light years. But the benefits of this cosmic magnifying glass go beyond just making distant objects visible. By magnifying these ancient galaxies and quasars, gravitational lensing allows scientists to study their structure, composition, and behavior in incredible detail. This is like having a front-row seat to the early universe, where we can observe the formation of the first stars and galaxies, and even trace the evolution of cosmic structures over time. One of the most exciting aspects of this magnification is its ability to reveal the universe's infancy. The light from these distant objects has traveled for billions of years to reach us, meaning we're seeing them as they were when the universe was young. By studying these ancient snapshots, astronomers can piece together the story of how the universe evolved, from the first moments after the Big Bang to the complex web of galaxies we see today. Gravitational lensing also plays a crucial role in understanding dark matter and dark energy. The way light bends around massive objects depends on the distribution of dark matter, and by studying these lensed images, scientists can map the invisible scaffolding of the cosmos. Additionally, the brightness and distance of these magnified objects provide clues about the rate of the universe's expansion, helping us unravel the mysteries of dark energy. In essence, gravitational lensing is more than just a tool for magnification. It's a window into the past and a key to understanding the universe's deepest secrets. By acting as a cosmic magnifying glass, it allows us to explore the farthest reaches of space and time, revealing the early universe in ways we never thought possible. Next, we'll explore how galaxy clusters, with their immense gravitational pull, serve as some of the most powerful lenses in the cosmos. Now, let's turn our attention to galaxy clusters, the heavyweight champions of gravitational lensing. These colossal structures, made up of hundreds or even thousands of galaxies bound together by gravity, are some of the most massive objects in the universe. And with that immense mass comes an equally immense gravitational pull, making galaxy clusters some of the most powerful natural lenses we know of. When light from a distant object passes near a galaxy cluster, the cluster's gravity bends and magnifies that light, often creating stunning visual effects. These can include multiple images of the same object, stretched arcs of light, or even complete rings, known as Einstein rings. The sheer scale of galaxy clusters means they can magnify objects that are incredibly far away, giving us a glimpse into the universe's earliest days. One of the most famous examples of a galaxy cluster acting as a gravitational lens is the Abell 1689 cluster. Located about 2.3 billion light-years from Earth, Abell 1689 is a true cosmic giant. Its immense mass distorts the light from galaxies behind it, creating a spectacular array of arcs and smeared images. In fact, Abell 1689 has been used to study some of the most distant galaxies ever observed, magnifying their light so that astronomers can analyze their properties in detail. But galaxy clusters don't just magnify distant objects, they also help us map the distribution of dark matter. Because dark matter doesn't emit light, it's invisible to traditional telescopes. However, its presence can be inferred by the way it bends light through gravitational lensing. By studying the distortions caused by galaxy clusters like Abell 1689, scientists can create detailed maps of dark matter, revealing the hidden structure of the universe. Galaxy clusters also play a key role in testing our understanding of gravity and cosmology. The way light bends around these massive objects provides a natural laboratory for studying the effects of general relativity on a cosmic scale. And because galaxy clusters are so massive, they can magnify objects that are otherwise too faint or distant to study, giving us a unique window into the universe's history. In essence, galaxy clusters are more than just collections of galaxies. They're cosmic magnifiers, dark matter mappers, and gravitational laboratories all rolled into one. Their immense power as gravitational lenses allows us to explore the universe in ways that would otherwise be impossible, revealing the secrets of the cosmos one bent beam of light at a time. Next, we'll dive into the Hubble Frontier Fields project, where galaxy clusters were used to peer deeper into the universe than ever before. Now, let's take a closer look at one of the most ambitious projects in the history of astronomy, the Hubble Frontier Fields. This groundbreaking initiative pushed the limits of what we thought was possible, using the power of gravitational lensing to peer deeper into the universe than ever before. By combining the incredible resolution of the Hubble Space Telescope with the natural magnification of galaxy clusters, the Hubble Frontier Fields project revealed galaxies so distant and faint that they would have otherwise remained hidden from our view. The project focused on 6 massive galaxy clusters, each acting as a natural telescope to magnify the light from galaxies behind them. These clusters, including Abell 2744 and Max J0416, were chosen for their immense gravitational pull, which bends and amplifies the light from even more distant objects. The result, a treasure trove of galaxies from the early universe, some of which existed when the cosmos was just a few 100 million years old. These ancient galaxies offer a glimpse into the universe's infancy, helping us understand how galaxies formed and evolved over billions of years. But the Hubble Frontier Fields didn't just rely on the galaxy clusters themselves. The project also included deep field observations of the regions surrounding these clusters, capturing light from galaxies that weren't magnified by lensing. This dual approach allowed astronomers to compare lensed and non-lensed galaxies, providing a more complete picture of the early universe. The data collected has been invaluable, shedding light on everything from the rate of star formation in young galaxies to the distribution of dark matter in the cosmos. One of the most remarkable discoveries from the Hubble Frontier Fields was the identification of some of the faintest and most distant galaxies ever observed. These galaxies, magnified by the gravitational lenses of the foreground clusters, appear as tiny, smudged dots of light. Yet they hold the key to understanding how the first galaxies formed and how they contributed to the reionization of the universe, a pivotal period when the first stars and galaxies lit up the cosmos, ending the so-called cosmic dark ages. The Hubble Frontier Fields project also demonstrated the incredible synergy between human ingenuity and the natural phenomena of the universe. By harnessing the power of gravitational lensing, astronomers were able to extend the reach of the Hubble Space Telescope far beyond its original capabilities. This collaboration between technology and nature has opened new doors for exploration, allowing us to study the universe in ways that were once thought impossible. As we continue to analyze the data from the Hubble Frontier Fields, we're uncovering more secrets about the early universe and the processes that shaped it. This project has not only deepened our understanding of galaxy formation, but also set the stage for future missions like the James Webb Space Telescope, which will build on these discoveries to explore even further into the cosmos. Next, we'll explore some of the most extreme gravitational lensing events ever observed, where the universe's most massive objects create mind-bending distortions of light. Now, let's turn our attention to some of the most extreme gravitational lensing events ever observed, where the universe's most massive objects create mind-bending distortions of light. These events push the boundaries of what we thought was possible, revealing the sheer power of gravity to warp spacetime and magnify the distant cosmos. One of the most striking examples is the galaxy cluster Max J0717.5 plus 3745. This colossal cluster, located billions of light-years away, is one of the most massive and complex gravitational lenses ever discovered. Its immense gravitational pull doesn't just bend light, it twists and stretches it into dramatic arcs and multiple images of the same background galaxies. In fact, Max J0717.5 plus 3745 is so massive that it's often referred to as a cosmic kaleidoscope, creating a stunning visual tapestry of the universe's distant past. But the extreme lensing effects don't stop there. Another remarkable example is the galaxy cluster known as Able 2204. This cluster's gravitational field is so powerful that it magnifies the light from galaxies behind it by up to 30 times, making faint objects visible that would otherwise be completely undetectable. Able 2204 has allowed astronomers to study some of the earliest galaxies in the universe, offering a rare glimpse into the cosmos when it was just a fraction of its current age. Then there's the galaxy cluster SDSS-J1004 plus 4112, which holds the record for one of the longest observed time delays in gravitational lensing. In this system, light from a distant quasar is bent around the cluster in such a way that it arrives at Earth at different times, creating a cosmic time machine of sorts. By studying these time delays, scientists can measure the expansion rate of the universe and gain insights into the nature of dark energy. These extreme lensing events aren't just visually stunning, they're also scientifically invaluable. They allow us to study the distribution of dark matter, measure the universe's expansion, and even test the predictions of Einstein's theory of general relativity on a cosmic scale. Each of these events serves as a reminder of the universe's ability to surprise and inspire, revealing the hidden connections between gravity, light, and the fabric of spacetime itself. As we continue to explore these extreme lensing events, we're not just uncovering the secrets of the universe, we're also pushing the limits of our own understanding. Next, we'll dive into how black holes, with their intense gravitational fields, create some of the most dramatic lensing effects in the cosmos. Now, let's shift our focus to one of the most fascinating players in the cosmic theater, black holes. These enigmatic objects, with their unimaginably strong gravitational fields, are not just cosmic vacuum cleaners, they're also some of the most powerful gravitational lenses in the universe. When light passes near a black hole, its intense gravity bends and distorts the light in ways that can create some of the most dramatic lensing effects we've ever observed. Imagine a black hole as a cosmic magnifying glass, but one that doesn't just bend light. It twists and warps it into bizarre shapes. Because black holes are so dense and compact, their gravitational fields are incredibly concentrated. This means they can create lensing effects that are far more extreme than those produced by galaxies or galaxy clusters. For example, if a star or galaxy happens to pass behind a black hole from our point of view, the black hole's gravity can magnify and distort the light, creating multiple images or even a full Einstein ring around the black hole itself. But black holes don't just create stunning visual effects, they also provide scientists with a unique tool to study their properties. By observing how light bends around a black hole, astronomers can measure its mass, spin, and even the structure of its event horizon. This is especially important for supermassive black holes, which lurk at the centers of galaxies. Gravitational lensing allows us to peer into the heart of these cosmic giants, revealing details that would otherwise remain hidden. One of the most groundbreaking examples of this is the first ever image of a black hole, captured by the Event Horizon Telescope in 2019. This historic image, which showed the shadow of the black hole at the center of the galaxy Messier 87, was made possible in part by gravitational lensing. The black hole's gravity bent the light from its surrounding accretion disk, creating a glowing ring that matched the predictions of Einstein's theory of general relativity. Black holes also play a key role in studying the universe's most extreme environments. For instance, when two black holes collide, the resulting gravitational waves can create ripples in spacetime that are detectable here on Earth. Gravitational lensing helps us study these events by magnifying the light from distant galaxies, allowing us to observe the aftermath of such cosmic collisions. In essence, black holes are not just gravitational powerhouses, they're also cosmic laboratories. Through gravitational lensing, they give us a front-row seat to some of the most extreme physics in the universe, from the warping of spacetime to the behavior of matter under unimaginable conditions. As we continue to explore these mysterious objects, we're not just uncovering the secrets of black holes, we're also gaining deeper insights into the very fabric of the cosmos. Next, we'll take a closer look at how gravitational lensing played a pivotal role in capturing that first iconic image of a black hole. Now, let's dive into one of the most monumental achievements in modern astronomy, the first ever image of a black hole. This groundbreaking moment, achieved by the Event Horizon Telescope in 2019, was not just a triumph of technology but also a testament to the power of gravitational lensing. The black hole at the center of the galaxy Messier 87, located 55 million light-years away, became the star of this cosmic show, and gravitational lensing played a crucial role in bringing its shadow into view. To capture this historic image, scientists relied on a global network of radio telescopes working together as one giant observatory. But even with this incredible setup, the black hole's immense distance and the faint light from its surroundings posed a significant challenge. This is where gravitational lensing stepped in. The black hole's intense gravity bent and magnified the light from its accretion disk, the swirling ring of superheated gas and dust orbiting it. This bending of light created a glowing ring around the black hole, a phenomenon predicted by Einstein's theory of general relativity. Without gravitational lensing, the faint light from the accretion disk might have been too dim to detect, making the image impossible to capture. The final image revealed a dark shadow at the center, surrounded by a bright, asymmetrical ring of light. This shadow is not the black hole itself, since black holes don't emit light, but rather the absence of light caused by the black hole's event horizon, the point of no return. The glowing ring, on the other hand, is the result of light being bent and twisted by the black hole's gravity, a direct consequence of gravitational lensing. This image not only confirmed decades of theoretical predictions, but also provided a stunning visual representation of one of the universe's most extreme objects. What makes this achievement even more remarkable is the precision required to capture it. The Event Horizon Telescope had to synchronize data from telescopes across the globe, accounting for the Earth's rotation and atmospheric interference. Gravitational lensing acted as a natural magnifying glass, amplifying the light and allowing scientists to piece together the image with unprecedented detail. This collaboration between human ingenuity and the laws of physics opened a new window into the study of black holes and the extreme environments they create. The first image of a black hole was more than just a scientific milestone. It was a moment that captured the world's imagination. It showed us the invisible, revealing the hidden heart of a distant galaxy, and proving once again that the universe is full of wonders waiting to be discovered. As we continue to explore the cosmos, gravitational lensing will remain an essential tool, helping us uncover even more secrets of these mysterious objects. Next, we'll explore how gravitational lensing has revolutionized the search for exoplanets, bringing us closer to finding worlds beyond our solar system. Now, let's shift our focus to how gravitational lensing has opened up a whole new frontier in the search for exoplanets. While most exoplanet discoveries come from methods like the transit technique or radial velocity, microlensing has proven to be a game changer, especially for finding planets that are otherwise invisible to us. Microlensing occurs when a smaller object, like a star or even a planet, passes in front of a more distant star, acting as a temporary magnifying glass. This brief but powerful effect can reveal the presence of exoplanets that are too far away or too faint to be detected by other means. One of the most remarkable aspects of microlensing is its ability to uncover planets in regions of space that are otherwise difficult to explore. For example, it has allowed astronomers to detect exoplanets in the galactic bulge, the densely packed central region of our Milky Way galaxy. These planets are often thousands of light years away, far beyond the reach of traditional detection methods. Microlensing doesn't rely on the brightness of the planet or its host star. Instead, it depends on the gravitational influence of the planet itself, making it an incredibly versatile tool. One of the most exciting discoveries made through microlensing is the detection of so-called rogue planets. These are planets that don't orbit any star but instead drift freely through space. Without a host star to illuminate them, rogue planets are nearly impossible to spot using conventional methods. However, microlensing can detect the subtle distortion of light caused by their gravity, revealing their presence. Some of these rogue planets are thought to have been ejected from their original star systems, while others may have formed independently in the cold, dark regions of space. Microlensing has also been instrumental in finding Earth-like planets in the habitable zones of their stars. While these planets are often too distant for detailed study, their discovery expands our understanding of how common or rare Earth-like worlds might be in the universe. For instance, in 2015, microlensing helped identify a planet with a mass similar to Earth's, orbiting a star in the galactic bulge. This discovery hinted at the possibility of countless other Earth-sized planets waiting to be found. What makes microlensing truly unique is its ability to detect planets across a wide range of masses and distances. From gas giants to small, rocky worlds, this technique has uncovered a diverse array of exoplanets, each adding a new piece to the puzzle of planetary formation and evolution. As we continue to refine our methods and expand our observations, microlensing promises to reveal even more about the hidden worlds scattered throughout our galaxy. Next, we'll explore how gravitational lensing has shed light on another mysterious population of objects, rogue planets, which wander through space without a star to call home. Now, let's take a closer look at one of the most intriguing discoveries made possible by gravitational microlensing: rogue planets. These mysterious worlds drift through the vastness of space without being tethered to any star, making them nearly invisible to traditional detection methods. But thanks to microlensing, we've been able to catch glimpses of these nomadic planets, revealing a fascinating aspect of our universe that was once hidden from view. Rogue planets, also known as free-floating planets, are thought to have either been ejected from their original star systems during chaotic gravitational interactions or formed independently in the cold, dark regions of interstellar space. Without a host star to illuminate them, they are incredibly difficult to detect using conventional techniques like the transit method or radial velocity. However, microlensing offers a unique solution. When a rogue planet passes in front of a distant star, its gravity bends and magnifies the star's light, creating a temporary brightening that astronomers can observe. This subtle but detectable effect allows us to identify these otherwise invisible worlds. One of the most remarkable aspects of rogue planets is their sheer abundance. Studies suggest that there could be billions of these free-floating planets scattered throughout our galaxy, outnumbering even the stars themselves. Some of these rogue planets are massive gas giants, while others are smaller, rocky worlds that might resemble Earth. The discovery of such a diverse population challenges our understanding of planetary formation and raises intriguing questions about how these planets came to be. Microlensing has also provided clues about the environments in which rogue planets exist. For instance, some of these planets have been found in the galactic bulge, the densely packed central region of the Milky Way. Others have been detected in the colder, more isolated regions of interstellar space. These findings suggest that rogue planets are not confined to a specific area, but are instead widespread throughout the galaxy. The study of rogue planets has profound implications for our understanding of the universe. They offer a glimpse into the chaotic processes that can eject planets from their star systems, as well as the possibility of planets forming in isolation. Some scientists even speculate that rogue planets could potentially harbor life, especially if they have subsurface oceans or thick atmospheres that trap heat. While this remains speculative, the discovery of these wandering worlds opens up exciting new avenues for exploration. As we continue to refine our microlensing techniques and expand our observations, the search for rogue planets promises to uncover even more about these enigmatic objects. Each discovery adds a new piece to the puzzle of planetary formation and evolution, reminding us just how diverse and dynamic our universe truly is. Next, we'll explore how gravitational lensing is shaping the future of astronomy, offering new tools and insights to unravel the mysteries of the cosmos. As we look ahead, the future of gravitational lensing is brighter than ever, thanks to a new generation of cutting-edge telescopes poised to transform our understanding of the cosmos. Leading the charge is the James Webb Space Telescope, a marvel of modern engineering designed to peer deeper into the universe than ever before. With its unprecedented sensitivity to infrared light, Webb will allow us to observe some of the earliest galaxies in the universe, magnified and distorted by gravitational lensing. This will provide invaluable insights into the formation and evolution of galaxies, as well as the distribution of dark matter that shapes their growth. Joining Webb in this cosmic quest is the Vera C. Rubin Observatory, set to begin its operations in the coming years. Unlike Webb, which focuses on detailed observations of specific targets, Rubin will conduct a sweeping survey of the entire sky, capturing vast amounts of data on gravitational lensing events. Its powerful camera, capable of imaging the entire visible sky every few nights, will detect subtle distortions in the shapes of distant galaxies caused by weak lensing. This will help scientists create detailed maps of dark matter and refine our understanding of how it influences the large-scale structure of the universe. Together, these telescopes will complement each other, offering a comprehensive view of gravitational lensing across different scales. Webb's high-resolution observations will reveal the intricate details of individual lensing events, while Rubin's wide-field surveys will uncover patterns and trends on a cosmic scale. This dual approach will enable astronomers to tackle some of the most pressing questions in cosmology, from the nature of dark energy to the origins of the universe itself. But the advancements don't stop there. Future missions such as the Nancy Grace Roman Space Telescope will further expand our capabilities, using gravitational lensing to study exoplanets, dark matter, and even the earliest moments after the Big Bang. These telescopes represent a new era of discovery, where gravitational lensing will play a central role in unraveling the mysteries of the universe. As these instruments come online, they will not only enhance our scientific knowledge, but also inspire a new generation of astronomers and space enthusiasts. The images and data they provide will captivate the public, offering a glimpse into the awe-inspiring beauty and complexity of the cosmos. With each new observation, we move closer to understanding the universe's most profound secrets, driven by the power of gravitational lensing and the ingenuity of human exploration. Next, we'll delve into how gravitational lensing is helping us measure the expansion of the universe, shedding light on one of the greatest mysteries in modern science. Now, let's turn our attention to one of the most profound mysteries in cosmology, the expansion of the universe, and how gravitational lensing is helping us unravel it. The universe isn't just expanding, it's doing so at an accelerating rate, a phenomenon driven by a mysterious force known as dark energy. But how do we measure something as vast and elusive as the universe's expansion? This is where gravitational lensing steps in as a powerful tool. Gravitational lensing allows scientists to observe distant objects like galaxies or quasars, whose light has been bent and magnified by massive objects in between. By studying these lensed images, astronomers can measure the distances to these faraway objects with remarkable precision. These measurements are crucial because they help us determine how fast the universe is expanding over time. Think of it like placing mile markers along a cosmic highway. Each lensed object gives us a snapshot of the universe's growth at different points in its history. One of the key ways gravitational lensing contributes to this is through time delays. When light from a distant object takes multiple paths around a massive lensing object, it arrives at Earth at slightly different times. By analyzing these time delays, scientists can calculate the distances involved and, in turn, infer the rate of expansion. This method has been used to refine our understanding of the Hubble constant, the number that describes how fast the universe is expanding. However, there's a twist. Different methods of measuring the Hubble constant have produced slightly different results, a discrepancy known as the Hubble tension. Gravitational lensing offers a unique way to cross-check these measurements, helping to resolve this cosmic puzzle, but the story doesn't end there. Gravitational lensing also provides clues about dark energy, the mysterious force driving the universe's accelerated expansion. By mapping the distribution of dark matter through weak lensing, scientists can infer how dark energy has influenced the growth of cosmic structures over billions of years. This helps us piece together the history of the universe's expansion and understand the role dark energy plays in shaping its future. As we continue to refine our techniques and gather more data, gravitational lensing will remain at the forefront of this cosmic detective work. It's not just about measuring distances or calculating rates, it's about uncovering the fundamental forces that govern the universe. And with each new discovery, we move closer to answering one of the biggest questions in science. What is the ultimate fate of our universe? Next, we'll explore the most massive objects in the cosmos that create gravitational lensing and how they shape our view of the universe. Now, let's shift our gaze to the true giants of the cosmos, the most massive objects that act as gravitational lenses. These colossal structures, like superclusters of galaxies, possess such immense gravitational pull that they bend and magnify light on an extraordinary scale. Superclusters are not just collections of galaxies, they are vast cosmic networks bound together by gravity, stretching across hundreds of millions of light years. When light from even more distant objects passes through these superclusters, it gets warped and amplified, creating some of the most dramatic lensing effects we've ever observed. One of the most famous examples is the Abell 1689 supercluster, a behemoth located about 2 billion light-years away. This supercluster is so massive that it acts like a cosmic magnifying glass, distorting the light from galaxies behind it into stunning arcs and rings. These lensed images allow astronomers to peer deeper into the universe than ever before, revealing galaxies that would otherwise be too faint to see. But Abell 1689 isn't just a spectacle, it's also a treasure trove of information. By studying how it bends light, scientists can map the distribution of dark matter within the supercluster, giving us clues about how these massive structures form and evolve. Another remarkable example is the Phoenix cluster, one of the most massive galaxy clusters known. Its gravitational lensing effects are so powerful that they've allowed astronomers to observe some of the earliest galaxies in the universe. These observations provide a glimpse into the universe's infancy, helping us understand how galaxies formed and grew over billions of years. The sheer mass of these superclusters doesn't just bend light, it also slows down time itself, a phenomenon predicted by Einstein's theory of general relativity. This time dilation effect, though subtle, adds another layer of complexity to our observations. The impact of these massive lenses goes beyond just magnifying distant objects. They also help us test the limits of our understanding of gravity and the universe's large-scale structure. For instance, the way light bends around superclusters can reveal whether our current models of dark matter and dark energy hold up under extreme conditions. These observations are pushing the boundaries of cosmology, challenging us to refine our theories and deepen our understanding of the cosmos. As we continue to study these cosmic giants, we're not just uncovering the secrets of the universe's most massive structures, we're also gaining new insights into the fundamental forces that shape everything around us. Next, we'll explore how supercomputers are revolutionizing our ability to simulate and interpret these incredible gravitational lensing events. Now, let's dive into the incredible role supercomputers play in unraveling the mysteries of gravitational lensing. These powerful machines are like the ultimate cosmic detectives, helping scientists make sense of the mind-bending distortions created by massive objects in space. Gravitational lensing simulations are incredibly complex, requiring calculations that take into account the mass, shape, and alignment of lensing objects, as well as the intricate paths light takes as it bends around them. Without supercomputers, these simulations would be nearly impossible to perform. Supercomputers allow researchers to create detailed models of gravitational lensing events, simulating how light from distant galaxies or quasars gets warped as it passes through massive galaxy clusters or black holes. These simulations are crucial for interpreting the real-world observations made by telescopes like Hubble or the James Webb Space Telescope. For example, when astronomers see a distorted arc or multiple images of a galaxy, supercomputers help them reconstruct what the original object looked like and determine the mass and distribution of the lensing object. This process is like solving a cosmic puzzle where every piece of data is essential for revealing the bigger picture. One of the most exciting applications of supercomputers in gravitational lensing is their ability to test and refine our understanding of dark matter. By simulating how dark matter halos around galaxies and clusters bend light, scientists can compare these simulations to actual observations. If the simulations match the real data, it gives us confidence in our models of dark matter. If they don't, it's a sign that we might need to rethink our theories. This back and forth between simulation and observation is driving some of the most groundbreaking discoveries in cosmology today. Supercomputers also enable researchers to explore hypothetical scenarios, such as what would happen if a supermassive black hole passed in front of a distant quasar, or how a galaxy cluster's lensing effects would change if its dark matter distribution were slightly different. These what-if experiments help scientists push the boundaries of our knowledge, uncovering new insights into the nature of gravity, space-time, and the universe itself. As we continue to develop more advanced supercomputers, their role in gravitational lensing research will only grow. They're not just tools for analyzing data, they're gateways to understanding the universe on a deeper level. Next, we'll explore how gravitational lensing interacts with the cosmic microwave background, the afterglow of the Big Bang, and what it tells us about the early universe. Now, let's turn our attention to one of the most fascinating intersections in cosmology, gravitational lensing and the cosmic microwave background. The cosmic microwave background, often referred to as the CMB, is the faint glow of light left over from the Big Bang, and it's one of the most important tools we have for understanding the early universe. But did you know that gravitational lensing can actually distort this ancient light, revealing even more secrets about the cosmos? When light from the CMB travels across the universe, it doesn't always take a straight path. Massive objects like galaxy clusters can bend this light, just as they bend light from distant galaxies. This means that the CMB we observe today isn't exactly the same as it was when it first emerged. Gravitational lensing subtly warps the CMB, creating tiny distortions that scientists can study to learn about the distribution of matter in the universe, both visible and dark. These distortions, known as CMB lensing, act like a cosmic fingerprint. By analyzing them, researchers can map out the large-scale structure of the universe, including the invisible web of dark matter that shapes everything we see. This is incredibly valuable because the CMB provides a snapshot of the universe when it was just a few 100,000 years old. Gravitational lensing allows us to connect that ancient snapshot to the universe we see today, bridging the gap between the early cosmos and its current state. One of the most exciting discoveries from studying CMB lensing is its ability to shed light on the properties of dark energy, the mysterious force driving the accelerated expansion of the universe. By measuring how lensing distorts the CMB, scientists can infer how much dark energy exists and how it has influenced the growth of cosmic structures over billions of years. This is a crucial piece of the puzzle in understanding the ultimate fate of the universe, but the story doesn't end there. CMB lensing also helps us test the fundamental laws of physics. For example, it provides a way to verify predictions made by Einstein's theory of general relativity on the largest scales. If the lensing patterns in the CMB match what the theory predicts, it strengthens our confidence in our understanding of gravity. If they don't, it could hint at new physics waiting to be discovered. As we continue to refine our observations of the CMB, gravitational lensing will remain an essential tool for unlocking the secrets of the early universe. It's a reminder that even the oldest light in the cosmos still has stories to tell, and with the help of advanced technology, we're just beginning to listen. Next, we'll take a closer look at some of the most breathtaking images of gravitational lensing ever captured, showcasing the beauty and complexity of this cosmic phenomenon. Now, let's shift our gaze to the breathtaking beauty of gravitational lensing, captured in some of the most iconic images ever taken by telescopes. These images aren't just visually stunning, they're also packed with scientific significance, offering us a glimpse into the intricate dance of light and gravity on a cosmic scale. One of the most famous examples is the Hubble Deep Field, an image that forever changed our understanding of the universe. By staring at a seemingly empty patch of sky for hours, the Hubble Space Telescope revealed thousands of galaxies, many of which were magnified and distorted by gravitational lensing. This single image opened a window into the early universe, showing us galaxies as they appeared billions of years ago, their light bent and twisted by massive objects in the foreground. It's a humbling reminder of just how vast and interconnected the cosmos truly is. Another jaw-dropping example is the cosmic horseshoe, a nearly perfect Einstein ring formed by the gravitational lensing of a distant galaxy. The light from this galaxy is bent so dramatically by a massive foreground galaxy that it appears as a glowing arc resembling a horseshoe. This rare alignment is not only a visual marvel, but also a treasure trove of information for astronomers, allowing them to study the properties of both the lensing galaxy and the distant one behind it. Then there's the galaxy cluster Able 1689, a gravitational lensing powerhouse. Its immense mass warps the light from galaxies far behind it, creating a mesmerizing tapestry of arcs and streaks. These distorted images act as cosmic magnifying glasses, bringing into view some of the faintest and most distant objects in the universe. Able 1689 is a prime example of how gravitational lensing can turn a single cluster of galaxies into a natural telescope, revealing details that would otherwise remain hidden. These images are more than just snapshots, they're stories. Each one tells us about the distribution of matter in the universe, the nature of dark matter, and the evolution of galaxies over billions of years. They also remind us of the artistry inherent in science, where the interplay of light, gravity, and time creates scenes of unparalleled beauty. As we marvel at these cosmic masterpieces, it's worth remembering that they're not just for scientists. They're for all of us, offering a chance to connect with the universe in a profound and personal way. Next, we'll explore how gravitational lensing is helping us uncover the mysteries of dark energy, the force shaping the fate of our universe. Now, let's turn our attention to one of the most profound mysteries of the cosmos: dark energy. This enigmatic force is responsible for the accelerated expansion of the universe, and gravitational lensing has become a powerful tool in our quest to understand it. By studying how light bends around massive objects, scientists can map the distribution of matter and energy across vast distances, offering clues about the nature of dark energy. Gravitational lensing allows astronomers to measure how the universe has expanded over time. When light from distant galaxies is bent by massive objects like galaxy clusters, it creates distortions that reveal the amount of matter and energy in the universe. By analyzing these distortions, researchers can track how the rate of expansion has changed, providing critical insights into the behavior of dark energy. This method has helped confirm that the universe isn't just expanding, it's doing so at an ever-increasing pace. One of the key projects using gravitational lensing to study dark energy is the Dark Energy Survey. This ambitious effort has mapped millions of galaxies, using their distorted shapes to measure the effects of dark energy on the large-scale structure of the universe. The data collected has been instrumental in refining our understanding of this mysterious force, suggesting that dark energy makes up about 70% of the universe's total energy content. But the search doesn't stop there. Upcoming missions like the Vera-C, Rubin Observatory, and the Euclid Space Telescope are set to take this research to new heights. These advanced instruments will observe billions of galaxies, using gravitational lensing to create the most detailed maps of the universe ever made. By pinpointing how dark energy influences the growth of cosmic structures, these projects aim to unravel its true nature, whether it's a property of space itself, as Einstein once proposed, or something entirely different. Gravitational lensing doesn't just help us see the universe, it helps us understand the forces shaping its destiny. As we continue to explore the mysteries of dark energy, this incredible phenomenon remains one of our most valuable tools, offering a window into the very fabric of reality. Next, we'll delve into how gravitational lensing allowed astronomers to observe the most distant supernova ever seen, a discovery that further illuminates the story of our expanding universe. Now, let's journey to one of the most remarkable discoveries made possible by gravitational lensing, the observation of the most distant supernova ever seen. This extraordinary event, nicknamed Reshaped, offers a glimpse into the early universe and showcases the incredible power of gravitational lensing as a cosmic magnifying glass. Reshaped was first spotted in the galaxy cluster Max J 1149, 5+2223, where the immense gravity of the cluster acted like a lens, bending and magnifying the light from a supernova that occurred billions of years ago. What made this discovery even more fascinating was that the supernova appeared not once but multiple times, thanks to the complex lensing effects of the cluster. This phenomenon, known as a time delay, allowed astronomers to observe the same supernova at different stages of its explosion, providing a rare opportunity to study the life cycle of these cosmic events in unprecedented detail. The discovery of Reshaped was a triumph of both technology and theory. Astronomers had predicted the supernova's reappearance based on their understanding of the cluster's gravitational lensing properties, and when it appeared again, it confirmed their calculations with stunning accuracy. This achievement not only demonstrated the predictive power of gravitational lensing, but also opened new doors for studying the early universe. By analyzing the light from Rifstal, scientists gained insights into the conditions of the cosmos when it was just a fraction of its current age. Rifstal's story is a testament to how gravitational lensing can turn the universe into a natural laboratory, allowing us to witness events that would otherwise remain hidden in the depths of space and time. As we continue to explore the cosmos, discoveries like this remind us of the profound ways in which gravity shapes our view of the universe. Next, we'll explore how gravitational lensing could provide clues about the existence of parallel universes or the multiverse, a concept that pushes the boundaries of our understanding even further. Now, let's venture into one of the most mind-bending possibilities in modern cosmology, how gravitational lensing might offer clues about the existence of parallel universes or the multiverse. This idea pushes the boundaries of our understanding, blending the mysteries of gravity with the speculative realms of theoretical physics. The multiverse theory suggests that our universe might be just one of countless others, each with its own unique physical laws and properties. While this concept remains largely theoretical, gravitational lensing could provide a rare window into testing its validity. One intriguing possibility is that gravitational lensing might reveal anomalies in the distribution of light or matter that could hint at the presence of other universes. For instance, if a massive object in our universe were to act as a lens, it might not only bend light from distant galaxies, but also potentially reveal distortions caused by the gravitational influence of a neighboring universe. Another fascinating angle involves the study of cosmic microwave background radiation, the afterglow of the Big Bang. Gravitational lensing can subtly alter this radiation, and some scientists speculate that unusual patterns in these distortions might point to interactions with other universes. While these ideas are still in their infancy, they highlight how gravitational lensing serves as a bridge between observable phenomena and the most speculative frontiers of science. The search for evidence of the multiverse through gravitational lensing is a testament to the power of curiosity and imagination in science. While we may not have definitive answers yet, the very possibility that lensing could unlock such profound secrets keeps astronomers and physicists eagerly exploring the cosmos. As we continue to push the limits of our knowledge, gravitational lensing remains one of our most powerful tools for peering into the unknown. Next, we'll dive into the role of quasars, the brightest objects in the universe, and how they play a crucial part in gravitational lensing studies. Now, shifting our focus to the dazzling beacons of the cosmos, let's explore the role of quasars in gravitational lensing. Quasars, short for quasi-stellar objects, are among the brightest and most energetic phenomena in the universe. Powered by supermassive black holes at the centers of distant galaxies, these cosmic powerhouses emit staggering amounts of light, making them ideal candidates for gravitational lensing studies. Because quasars are so luminous, their light can travel billions of light years across the universe, only to be bent and magnified by massive objects like galaxies or galaxy clusters acting as gravitational lenses. This intense light allows astronomers to study not only the quasars themselves, but also the properties of the lensing objects in between. For example, when a quasar's light is split into multiple images by a gravitational lens, scientists can measure the time delays between these images to learn about the distribution of dark matter in the lensing galaxy or cluster. Quasars also serve as cosmic flashlights, illuminating the structure of the universe on the largest scales. Their light can reveal the presence of otherwise invisible dark matter halos or even help map the cosmic web, the vast network of galaxies and dark matter that spans the cosmos. Additionally, because quasars are so far away, their lensed images provide a unique opportunity to study the early universe, offering glimpses into how galaxies and black holes formed and evolved over billions of years. The combination of their extreme brightness and their distance makes quasars invaluable tools for probing the mysteries of gravity, dark matter, and the large-scale structure of the universe. As we continue to observe these brilliant objects through the lens of gravity, they illuminate not just the cosmos but also the profound connections between light, matter, and the fabric of spacetime itself. Next, we'll uncover some of the most extreme time delays observed in gravitational lensing, where light from the same object arrives at different times, creating a cosmic time-lapse effect. Now, let's step into the fascinating world of cosmic time delays, where the universe plays tricks with light and time. One of the most striking examples of this phenomenon is the quasar known as SDSS J1004 plus 4112. This distant quasar, located billions of light-years away, has been gravitationally lensed by a massive galaxy cluster, creating not just one but 4 distinct images of the same quasar. What makes this event extraordinary is the time delay between these images. Due to the different paths the light takes around the lensing cluster, the images of the quasar appear to us at different times, with delays that can span weeks, months, or even years. For instance, in the case of SDSS J1004 plus 4112, the time delays between the images range from several weeks to over a year. This cosmic time-lapse effect allows astronomers to study the quasar's behavior over time, almost as if they were watching a replay of its activity. By analyzing these delays, scientists can measure the distribution of mass in the lensing galaxy cluster, including the elusive dark matter that makes up most of its mass. These observations provide critical insights into the structure and evolution of galaxy clusters, as well as the nature of dark matter itself. Another remarkable example is the quasar known as He 0435-1223, which exhibits time delays of up to several years between its lensed images. These extreme delays are not just curiosities, they are powerful tools for probing the universe. By studying how light from the same object arrives at different times, astronomers can test theories of gravity, refine measurements of the universe's expansion rate, and even uncover hidden details about the lensing objects themselves. These time delays also offer a unique window into the variability of quasars. Since quasars can flicker and change brightness over time, the delayed images allow scientists to observe these changes multiple times, providing a deeper understanding of the processes powering these cosmic beacons. It's like having a natural time machine where the universe itself bends light and time to reveal its secrets. As we continue to explore the universe's most extreme gravitational lensing events, these time delays remind us of the intricate dance between light, gravity, and time. Next, we'll delve into how gravitational lensing helps us map the shape of the universe itself, uncovering the cosmic geometry that defines our existence. Now, let's turn our attention to how gravitational lensing reveals the very shape of the universe itself. One of the most profound questions in cosmology is understanding the geometry of the cosmos, whether it's flat, curved, or shaped in some other way. Gravitational lensing plays a crucial role in answering this question by acting as a cosmic measuring tool. When light from distant objects is bent by massive structures like galaxy clusters, the way it bends and the patterns it creates can tell us a lot about the universe's overall shape. For example, if the universe were perfectly flat, light would bend in predictable, straightforward ways. But if the universe had a curved geometry, the bending of light would follow different patterns, creating distortions that scientists can measure. By studying these distortions in gravitational lensing events, astronomers can map the large-scale structure of the universe and determine its geometry. This is like using a giant cosmic ruler to measure the curvature of space itself. One of the key ways scientists use gravitational lensing to study the universe's shape is by analyzing the distribution of dark matter. Dark matter doesn't emit light, but its gravitational effects can bend light from distant objects. By mapping how light is distorted around massive galaxy clusters, researchers can infer the distribution of dark matter and, in turn, understand how it influences the universe's geometry. This has led to some groundbreaking discoveries, such as confirming that the universe is remarkably flat on large scales, consistent with the predictions of the Big Bang theory. But the story doesn't end there. Gravitational lensing also helps scientists study the universe's expansion and the role of dark energy, the mysterious force driving that expansion. By observing how lensing events change over time, astronomers can measure how quickly the universe is stretching and how its shape evolves. This provides critical insights into the ultimate fate of the cosmos, whether it will continue expanding forever, slow down, or even collapse. As we piece together these cosmic clues, gravitational lensing emerges as one of the most powerful tools for understanding the universe's shape and structure. It's a reminder that even the most distant light can reveal the deepest truths about our existence. Next, we'll explore how the most massive black holes in the universe create some of the most extreme gravitational lensing effects, bending light in ways that challenge our understanding of space and time. Now, let's shift our focus to the most massive black holes in the universe and the extraordinary gravitational lensing effects they create. Black holes, with their immense gravitational pull, are some of the most extreme cosmic objects capable of bending light in ways that defy imagination. When we talk about black holes at the centers of active galaxies, we're dealing with supermassive black holes monsters that can weigh billions of times the mass of our Sun. These colossal objects don't just swallow light, they warp the very fabric of spacetime around them, creating some of the most dramatic lensing effects ever observed. Take, for instance, the supermassive black hole at the heart of the galaxy Messier 87, famously imaged by the Event Horizon Telescope. This black hole's gravitational field is so intense that it bends light from its surroundings into a glowing ring, a phenomenon known as an Einstein ring. But that's just the tip of the iceberg. In active galaxies where supermassive black holes are surrounded by swirling disks of gas and dust, the lensing effects can become even more complex. Light from stars or quasars behind these black holes can be stretched, magnified, or even split into multiple images, creating a cosmic kaleidoscope. One of the most fascinating aspects of these extreme lensing events is how they allow us to study black holes themselves. By observing how light bends around these objects, scientists can measure their mass, spin, and even the structure of their event horizons. For example, the lensing effects around the black hole in the galaxy SDSS-J 1004 plus 4112 have revealed multiple images of a distant quasar, each appearing at different times due to the bending of spacetime. This time delay provides a unique window into the black hole's properties and the nature of gravity itself. But the lensing effects of supermassive black holes aren't just scientific curiosities, they're also cosmic tools. By studying how these black holes distort light, astronomers can probe the environments around them, uncovering details about the galaxies they inhabit and the dark matter that surrounds them. In some cases, the lensing effects are so extreme that they magnify distant objects behind the black hole, allowing us to see galaxies and quasars that would otherwise be too faint to detect. As we continue to explore these cosmic giants, one thing becomes clear. Black holes are not just destructive forces, they're also cosmic lenses that reveal the hidden depths of the universe. Next, we'll dive into how gravitational lensing could help us detect primordial black holes, hypothetical objects that may have formed in the earliest moments of the universe. Now, let's turn our attention to one of the most intriguing mysteries of the cosmos: primordial black holes. These hypothetical objects are thought to have formed in the earliest moments of the universe, long before stars or galaxies even existed. Unlike the supermassive black holes we've discussed, primordial black holes could range in size from tiny, subatomic scales to masses thousands of times that of our Sun. But here's the catch: they've never been directly observed. So how do we search for something so elusive? Enter gravitational lensing. gravitational lensing offers a unique way to detect these ancient cosmic relics. If a primordial black hole passes between us and a distant star or galaxy, its immense gravitational field could bend and magnify the light from that background object. This temporary brightening, known as microlensing, could serve as a telltale sign of a primordial black hole's presence. The key lies in the duration and pattern of the lensing event. Because primordial black holes are expected to be much smaller than their supermassive counterparts, their lensing effects would be brief but detectable with precise observations. One of the most exciting aspects of this search is what it could reveal about the early universe. If primordial black holes exist, they could provide clues about the conditions just after the Big Bang, offering insights into the formation of the first structures in the cosmos. They might even help explain one of the greatest mysteries in modern physics: dark matter. Some scientists speculate that primordial black holes could make up a significant portion of dark matter, the invisible substance that holds galaxies together. Current and future telescopes like the Vera-C Rubin Observatory are poised to play a crucial role in this search. By scanning vast regions of the sky for microlensing events, astronomers hope to uncover evidence of these ancient objects. Each detection would not only confirm their existence but also open a new window into the universe's infancy. As we continue to explore the cosmos, the search for primordial black holes reminds us that some of the universe's most profound secrets may still be hidden in plain sight, waiting to be revealed through the lens of gravity. Next, we'll explore how neutron stars, with their intense gravitational fields, also contribute to the fascinating world of gravitational lensing. Now, shifting our gaze to another cosmic heavyweight, let's explore the role of neutron stars in the phenomenon of gravitational lensing. Neutron stars are the remnants of massive stars that have exploded in supernova, leaving behind an incredibly dense core. Imagine squeezing the mass of our Sun into a sphere no larger than a city. This is the mind-bending density of a neutron star. With such immense gravity packed into such a small space, neutron stars can bend the fabric of spacetime, creating their own subtle lensing effects. While neutron stars don't produce the dramatic distortions seen with galaxy clusters or supermassive black holes, their gravitational fields are still powerful enough to warp the light from background objects. This effect, though smaller in scale, is no less fascinating. For instance, if a neutron star passes in front of a distant star, it can briefly magnify the star's light, creating a microlensing event. These events are much shorter and less intense than those caused by larger objects, but they provide valuable insights into the properties of neutron stars themselves. One of the most intriguing aspects of neutron star lensing is its potential to reveal details about their structure and composition. By studying how light bends around these ultra-dense objects, scientists can infer information about their mass, size, and even the exotic states of matter that might exist within them. This is particularly exciting because neutron stars are thought to contain matter in forms that cannot be replicated on Earth, offering a unique window into the extremes of physics. Moreover, neutron stars often emit powerful beams of radiation known as pulsars, which can also be affected by their gravitational fields. In some cases, the lensing effect can amplify or distort these beams, providing additional clues about the star's environment and the nature of spacetime itself. While these observations are challenging due to the small scale of the effects, advancements in telescope technology are making it increasingly possible to detect and study them. As we continue to probe the universe, neutron stars remind us that even the smallest players in the cosmic arena can have a profound impact on our understanding of gravity and the fabric of reality. Next, we'll delve into how gravitational lensing provides insights into the ultimate fate of the universe, shedding light on whether it will expand forever or collapse in on itself. Now, let's turn our attention to one of the most profound questions in cosmology. What is the ultimate fate of the universe? gravitational lensing, as it turns out, plays a crucial role in helping scientists unravel this cosmic mystery. By studying how light bends around massive objects, researchers can gather clues about the universe's expansion and whether it will continue to grow indefinitely or eventually collapse in on itself. One of the key ways gravitational lensing contributes to this understanding is through its ability to measure the distribution of dark matter and dark energy. Dark energy, the mysterious force driving the accelerated expansion of the universe, leaves its imprint on the way light is bent by massive objects. By analyzing the distortions caused by gravitational lensing, scientists can map the influence of dark energy across vast cosmic distances. This data helps refine models of the universe's expansion and provides insights into whether dark energy will dominate forever, leading to an ever-expanding cosmos, or if gravity might eventually reverse this expansion, causing the universe to collapse in a big crunch. Another fascinating aspect is how gravitational lensing allows us to observe distant supernovae, which serve as cosmic mile markers. These supernovae, when magnified by lensing, provide precise measurements of the universe's expansion rate over time. By comparing these observations with theoretical predictions, scientists can test different scenarios for the universe's fate. For instance, if the expansion rate slows down significantly in the future, it could hint at a universe destined to collapse. On the other hand, if the acceleration continues unabated, it suggests a universe that will expand forever, growing colder and more diffuse. Gravitational lensing also helps us understand the role of dark matter in shaping the universe's destiny. Dark matter, which makes up most of the universe's mass, influences the growth of cosmic structures like galaxies and clusters. By studying how lensing distorts the light from these structures, scientists can infer the amount and distribution of dark matter, which in turn affects the gravitational forces that could either slow down or accelerate the universe's expansion. As we piece together these clues, gravitational lensing emerges as a powerful tool for peering into the distant future of our universe. While the ultimate fate remains uncertain, the insights gained from this phenomenon bring us closer to answering one of the most profound questions in science. Next, we'll explore some of the most extreme magnification events ever observed, where gravitational lensing has allowed us to see incredibly faint and distant objects in unprecedented detail. Now, let's zoom in on some of the most astonishing feats of gravitational lensing events where the magnification is so extreme that it reveals objects otherwise invisible to even our most powerful telescopes. These instances of extreme magnification are like nature's own high-powered zoom lens, bringing into view some of the faintest and most distant objects in the universe. One remarkable example is the galaxy cluster known as Max J 1149, 5 plus 2223. This cluster acts as a colossal gravitational lens, magnifying the light from a background galaxy so dramatically that it appears multiple times in a single image. But what makes this event truly extraordinary is the detection of a single star, nicknamed Icarus, located nearly 9 billion light-years away. Thanks to the extreme magnification caused by the cluster, astronomers were able to observe this star in unprecedented detail, a feat that would have been impossible without the lensing effect. This discovery not only highlights the power of gravitational lensing, but also opens up new possibilities for studying individual stars in the early universe. Another stunning example is the galaxy cluster Able 370, often referred to as the Dragon, due to the striking arc of light it creates. This cluster magnifies the light from a distant galaxy, making it appear as a long, stretched arc. The magnification here is so intense that it allows astronomers to study the galaxy's structure and composition in ways that would otherwise be out of reach. This kind of extreme magnification provides a rare glimpse into the formation and evolution of galaxies in the early universe, offering clues about how these cosmic structures came to be. Perhaps one of the most extreme cases of magnification comes from the galaxy cluster SDSS Joan 1100 plus 4641. This cluster magnifies the light from a distant quasar by a factor of more than 50, making it one of the most magnified objects ever observed. The quasar, which would typically be too faint to detect, becomes visible thanks to the lensing effect, allowing scientists to study its properties and gain insights into the conditions of the early universe. These extreme magnification events are not just scientific curiosities, they are windows into the distant past, enabling us to observe objects that would otherwise remain hidden. By studying these magnified images, astronomers can piece together the history of the universe, from the formation of the first stars and galaxies to the evolution of cosmic structures. As we continue to explore these phenomena, gravitational lensing promises to reveal even more secrets of the cosmos, pushing the boundaries of what we thought was possible. Next, we'll delve into how gravitational lensing could play a role in the search for extraterrestrial life, magnifying distant exoplanets and bringing us closer to answering one of humanity's most profound questions. Now, let's turn our attention to one of the most exciting possibilities in the realm of gravitational lensing, its potential role in the search for extraterrestrial life. Imagine a scenario where the universe itself acts as a giant magnifying glass, bringing distant exoplanets into view with unprecedented clarity. This is exactly what gravitational lensing could offer in the quest to find life beyond Earth. When a massive object like a galaxy or a black hole aligns perfectly between us and a distant exoplanet, it can magnify the planet's light, making it far easier to study. This magnification allows astronomers to analyze the planet's atmosphere in detail, searching for signs of habitability such as water vapor, oxygen, or even methane gases that could indicate the presence of life. Without gravitational lensing, many of these distant worlds would remain too faint and small to observe with current technology. One of the most promising aspects of this technique is its ability to magnify planets that orbit stars far beyond our own galaxy. While most exoplanet discoveries so far have been within our Milky Way, gravitational lensing could extend our reach to other galaxies, opening up entirely new frontiers in the search for life. For example, a planet magnified by a distant galaxy cluster could reveal details about its atmosphere and surface conditions, providing clues about whether it could support life as we know it. But the potential doesn't stop there. Gravitational lensing could also help us detect smaller, Earth-like planets that are often overshadowed by the brightness of their host stars. By magnifying these planets, astronomers can study their atmospheres for biosignatures, chemical markers that might indicate the presence of living organisms. This could bring us closer to answering one of humanity's most profound questions. Are we alone in the universe? As we continue to refine our techniques and develop more advanced telescopes, gravitational lensing could become a cornerstone in the search for alien life. By harnessing the power of this natural phenomenon, we might one day discover a world teeming with life, hidden in the depths of space. Next, we'll explore how dark matter halos around galaxies contribute to gravitational lensing and help map the invisible structures that shape our universe. Now, shifting our focus to the invisible architects of the cosmos, let's explore how dark matter halos play a crucial role in gravitational lensing. These halos, vast clouds of dark matter that envelop galaxies, are invisible to telescopes because they don't emit light. Yet, their immense gravitational influence shapes the way light bends around galaxies, making them key players in the lensing phenomenon. When light from a distant object passes near a galaxy, it doesn't just interact with the visible stars and gas, it's also affected by the galaxy's dark matter halo. This halo, which can extend far beyond the galaxy's visible edge, warps spacetime even more dramatically than the galaxy itself. As a result, the halo amplifies the lensing effect, creating distortions that reveal its presence and distribution. By studying these distortions, astronomers can map the dark matter halos around galaxies, This mapping provides critical insights into how dark matter is distributed across the universe. For instance, some halos are more concentrated at the center, while others are spread out, offering clues about how galaxies form and evolve over time. These observations also help scientists test theories about the nature of dark matter itself, a substance that makes up about 85% of the universe's mass but remains one of its greatest mysteries. One of the most fascinating aspects of dark matter halos is their ability to create multiple images of the same background object. In some cases, a single distant galaxy or quasar can appear as multiple arcs or even a complete ring around the lensing galaxy, a phenomenon known as an Einstein ring. These intricate patterns are direct evidence of the halo's gravitational influence, allowing astronomers to measure its mass and structure with remarkable precision. As we continue to study these halos, gravitational lensing serves as a powerful tool to peer into the invisible framework of the universe. By unraveling the secrets of dark matter, we gain a deeper understanding of the cosmic web that connects galaxies and shapes the large-scale structure of the cosmos. Next, we'll delve into how gravitational lensing provides clues about the moments after the Big Bang, shedding light on the origins of the universe itself. Now, let's take a step back in time, way back to the very beginnings of the universe. Gravitational lensing doesn't just help us see distant galaxies or map dark matter. It also offers a unique window into the moments following the Big Bang. By studying how light bends around massive objects, scientists can uncover clues about the early universe's structure, density, and even the seeds of galaxy formation. One of the most remarkable ways gravitational lensing connects us to the Big Bang is through its impact on the cosmic microwave background, or CMB. The CMB is the faint afterglow of the Big Bang, a snapshot of the universe when it was just 380,000 years old. Gravitational lensing subtly distorts this ancient light as it travels through the cosmos, bending it around massive structures like galaxy clusters. These distortions, though tiny, carry valuable information about the distribution of matter in the early universe. By analyzing these lensing effects on the CMB, astronomers can reconstruct the conditions of the universe when it was in its infancy. For example, they can measure how matter was distributed and how it clumped together, forming the first seeds of galaxies and galaxy clusters. This helps scientists test theories about how the universe expanded and evolved in its earliest moments, shedding light on processes like inflation, a rapid expansion thought to have occurred just fractions of a second after the Big Bang. Gravitational lensing also allows us to study the universe's first light sources, such as the earliest stars and galaxies. These objects are so distant and faint that they would be nearly impossible to observe without the magnifying effect of lensing. By amplifying their light, lensing acts like a time machine, bringing us closer to understanding how the first structures in the universe formed and how they influenced the cosmos we see today. In essence, gravitational lensing serves as a bridge between the present and the primordial past. It helps us piece together the story of the universe's birth and growth, offering insights into the fundamental forces and processes that shaped everything we know. As we continue to explore these connections, we move closer to answering some of the most profound questions about our cosmic origins. Next, we'll look at how perfect alignments in the cosmos create some of the most dramatic and awe-inspiring lensing effects ever observed. Now, let's turn our attention to one of the most breathtaking aspects of gravitational lensing: perfect cosmic alignments. When a massive object like a galaxy cluster aligns precisely between a distant light source and Earth, the result is nothing short of spectacular. These rare alignments create some of the most dramatic and visually stunning lensing effects in the universe, offering astronomers a front-row seat to phenomena that would otherwise remain hidden. One of the most famous examples of such an alignment is the Einstein cross, a quasar located billions of light-years away. Here, the light from the quasar is bent and split into 4 distinct images by the gravitational pull of a foreground galaxy. This perfect alignment forms a cross-like pattern, a striking demonstration of how gravity can warp and magnify light. The Einstein cross not only captivates with its beauty, but also provides valuable data about the mass distribution of the lensing galaxy and the properties of the distant quasar. Another remarkable case is the cosmic horseshoe, a nearly complete ring of light formed by a distant galaxy lensed by a massive foreground cluster. This rare alignment creates a near-perfect Einstein ring, a phenomenon predicted by Einstein's theory of general relativity. The cosmic horseshoe is one of the largest and most complete rings ever observed, offering a unique opportunity to study the distant galaxy in extraordinary detail. These extreme alignments are more than just cosmic curiosities, they are powerful tools for science. By studying the distortions and magnifications created by perfect alignments, astronomers can measure the mass of the lensing objects with incredible precision. They can also probe the properties of the distant light sources, such as their size, shape, and composition, in ways that would be impossible without the lensing effect. What makes these alignments so extraordinary is their rarity. The chances of a distant object, a massive lens, and Earth lining up so precisely are incredibly slim. Yet, when they do, the results are awe-inspiring, revealing the universe's hidden details in ways that challenge our understanding and ignite our curiosity. As we continue to search for these perfect alignments, we uncover not only the beauty of the cosmos but also the intricate workings of gravity itself. Next, we'll explore how gravitational lensing can even affect the apparent speed of light, opening up new avenues for understanding the fabric of spacetime. Now, let's shift our focus to a fascinating aspect of gravitational lensing that challenges our understanding of one of the universe's most fundamental constants, the speed of light. While the speed of light in a vacuum is always constant, gravitational lensing can create the illusion that light from distant objects is traveling at different speeds. This effect doesn't mean light itself is speeding up or slowing down, but rather that the path it takes through warped spacetime can make it appear to do so. Imagine light from a distant quasar traveling toward Earth. If a massive object like a galaxy cluster lies between the quasar and us, its gravity bends the light's path. This bending can cause the light to take a longer or more convoluted route to reach us, depending on the alignment of the objects. As a result, light from the same quasar can arrive at Earth at slightly different times, even though it all started its journey simultaneously. This phenomenon, known as a time delay, can make it seem as though the light is traveling at varying speeds. One of the most famous examples of this effect is seen in the quasar SDSS J1004+4112, where light from the same object arrives at Earth with delays of several years. These time delays provide astronomers with a unique opportunity to test Einstein's theory of general relativity with incredible precision. By measuring the differences in arrival times, scientists can map the distribution of mass in the lensing galaxy cluster and even calculate the expansion rate of the universe. But the implications go even deeper. These observations also help us understand the nature of spacetime itself. The fact that light can take multiple paths and arrive at different times reinforces the idea that spacetime is not a static stage but a dynamic, flexible fabric shaped by mass and energy. Gravitational lensing, in this way, acts as a cosmic laboratory, allowing us to probe the very foundations of physics. As we continue to study these effects, we gain not only a deeper appreciation for the elegance of Einstein's theories, but also new tools to explore the universe's most profound mysteries. Next, we'll delve into how supernova, when magnified by gravitational lensing, offer critical insights into the expansion of the universe and the enigmatic force known as dark energy. Now, let's turn our attention to one of the most explosive and illuminating events in the cosmos, supernova. and how gravitational lensing transforms them into powerful tools for understanding the universe. When a supernova occurs, it releases an immense burst of light, often outshining entire galaxies for a brief moment. But when a massive object like a galaxy cluster lies between the supernova and Earth, gravitational lensing can magnify and distort this light, creating multiple images or even time-delayed versions of the same explosion. These lensed supernovae are like cosmic stopwatches. Because the light from the supernova takes different paths around the lensing object, it arrives at Earth at different times. By measuring these time delays, astronomers can calculate the expansion rate of the universe with remarkable precision. This is especially valuable because supernovae are what scientists call standard candles, objects with known brightness that allow us to measure distances across the cosmos. When combined with gravitational lensing, they become even more powerful, offering insights into the mysterious force driving the universe's accelerated expansion, dark energy. One of the most famous examples of this is the supernova known as Reshaped, the first supernova ever observed with multiple images due to gravitational lensing. Discovered in the galaxy cluster Max J1149+2223, Reshaped appeared in 4 distinct locations around the cluster, each image representing a different path the light took. Astronomers were even able to predict when a 5th image would appear years later, thanks to their understanding of the lensing effect. This remarkable event not only confirmed the predictions of general relativity, but also provided a rare opportunity to study the properties of dark energy in greater detail. But the role of supernova in gravitational lensing goes beyond just measuring distances. By analyzing the light from these explosions, scientists can also study the distribution of dark matter in the lensing galaxy clusters. The way the light bends and the time delays it experiences reveal the mass and structure of the clusters, helping us map the invisible scaffolding of the universe. As we continue to observe more lensed supernova, we gain a clearer picture of how the universe has expanded over time and how dark energy influences its fate. These cosmic explosions, magnified by the universe's own gravitational lenses, are not just spectacular events. They are key to unlocking some of the deepest mysteries of our cosmos. Next, we'll explore how gravitational lensing could even help us detect one of the most elusive and mind-bending concepts in physics, wormholes. Now, let's venture into one of the most intriguing possibilities in the realm of gravitational lensing, its potential role in the search for wormholes. Wormholes, often depicted in science fiction as shortcuts through spacetime, are hypothetical tunnels that could connect distant parts of the universe or even different universes entirely. While they remain purely theoretical for now, gravitational lensing might offer a way to detect these cosmic shortcuts if they exist. Imagine a wormhole as a bridge between 2 points in spacetime. If light from a distant object passes near a wormhole, the intense gravitational field around it could bend and magnify the light, much like a massive galaxy or black hole would. However, the lensing effect created by a wormhole would have unique characteristics. For instance, instead of producing multiple images or arcs, a wormhole might create a distinctive pattern of light distortion, such as a ring with unusual symmetries or unexpected brightness variations. These anomalies could serve as telltale signs of a wormhole's presence. Scientists have proposed that by carefully analyzing the light from distant quasars or galaxies, they might spot these unusual lensing patterns. Advanced telescopes and observatories equipped with cutting-edge technology could scan the skies for these subtle distortions. If detected, such a discovery would revolutionize our understanding of space-time and open up entirely new avenues for exploring the cosmos. Of course, the search for wormholes is still in its infancy, and many challenges remain. Wormholes, if they exist, are likely incredibly rare and difficult to distinguish from other lensing objects. But the idea that gravitational lensing could one day help us uncover these cosmic tunnels is a thrilling prospect. It reminds us that the universe is full of mysteries waiting to be unraveled, and gravitational lensing is one of our most powerful tools for peering into the unknown. As we continue to push the boundaries of our knowledge, the interplay between gravitational lensing and exotic phenomena like wormholes keeps us dreaming of what lies beyond the horizon of our current understanding. Next, we'll delve into some of the most extreme distortions caused by gravitational lensing, where the universe's warped spacetime creates breathtaking and mind-bending visuals. Now, let's shift our focus to some of the most jaw-dropping visual spectacles in the universe: gravitational lensing events that create extreme distortions. These cosmic phenomena push the boundaries of what we thought possible, bending light in ways that defy imagination and leave us in awe of the universe's complexity. One of the most striking examples of extreme distortion is the formation of Einstein arcs. These are long, curved streaks of light that appear when a massive object, like a galaxy cluster, bends the light from a background galaxy into a nearly perfect arc. One of the most famous examples is the Hubble 370 galaxy cluster, which creates a stunning arc known as the Dragon. This arc is actually the distorted image of a galaxy located billions of light years behind the cluster, stretched and magnified by the cluster's immense gravitational pull. But the distortions don't stop there. In some cases, gravitational lensing can create multiple images of the same object. This happens when light from a distant source, like a quasar or galaxy, takes different paths around the lensing object, resulting in several distinct images. A classic example is the Einstein cross, where a single quasar appears as 4 separate images arranged in a cross-like pattern around a foreground galaxy. This mesmerizing effect not only showcases the power of gravitational lensing, but also provides astronomers with a unique opportunity to study the same object from multiple angles. Another mind-bending example is the phenomenon of giant arcs, where entire galaxies are stretched into massive, luminous curves. The galaxy cluster MAX J0717, for instance, is home to one of the largest and most complex gravitational lenses ever observed. Its immense mass distorts the light from background galaxies into sweeping arcs and intricate patterns, creating a cosmic tapestry that reveals the hidden structure of the universe. These extreme distortions are more than just visual marvels, they're also invaluable tools for scientists. By studying the shapes and positions of these arcs and multiple images, astronomers can map the distribution of dark matter in the lensing objects and gain insights into the large-scale structure of the cosmos. Each distorted image is like a puzzle piece, helping us piece together the grand picture of the universe. As we marvel at these extreme distortions, we're reminded of just how much the universe can surprise us. From arcs that stretch across the sky to multiple images of a single quasar, gravitational lensing continues to reveal the hidden beauty and complexity of the cosmos. Next, we'll explore how these distortions help us map the cosmic web, the vast network of galaxies and dark matter that shapes the universe. Now, let's take a closer look at how gravitational lensing unveils one of the most fascinating structures in the cosmos, the cosmic web. This vast network, made up of galaxies, dark matter, and immense voids, forms the backbone of the universe's large-scale structure. Gravitational lensing acts as a powerful tool, allowing scientists to map this intricate web and understand how it shapes the cosmos. When light from distant galaxies passes through the cosmic web, it gets bent and distorted by the gravitational pull of dark matter and galaxy clusters along its path. These distortions reveal the presence and distribution of dark matter, which is otherwise invisible to us. By analyzing these subtle changes in the light, astronomers can create detailed maps of the cosmic web, showing how galaxies and dark matter are interconnected across billions of light years. One of the most remarkable aspects of this mapping is how it highlights the filamentary structure of the universe. These filaments, made up of dark matter and gas, act like cosmic highways, guiding the formation and movement of galaxies. Gravitational lensing allows us to see these filaments in action, showing how they connect galaxy clusters and feed the growth of superclusters, the largest structures in the universe. For example, the Hubble Space Telescope has captured stunning images of lensed galaxies that trace the outlines of these filaments, providing a glimpse into the cosmic web's intricate design. These observations not only confirm the existence of dark matter, but also help us understand how it influences the evolution of the universe over time. By mapping the cosmic web, gravitational lensing also sheds light on the universe's expansion and the role of dark energy. The way light bends and travels through the web provides clues about the rate at which the universe is stretching, offering insights into the forces driving its accelerated expansion. As we piece together these cosmic maps, we gain a deeper appreciation for the universe's complexity and beauty. Gravitational lensing doesn't just show us the cosmic web, it helps us understand how everything in the universe is connected, from the tiniest galaxies to the largest superclusters. Next, we'll explore how cutting-edge technology, like artificial intelligence, is revolutionizing the way we analyze and interpret these cosmic phenomena. Now, let's shift our focus to how modern technology is transforming our understanding of gravitational lensing. Artificial intelligence, or AI, has become an indispensable tool in analyzing the vast amounts of data generated by gravitational lensing observations. With its ability to process complex information at incredible speeds, AI is helping astronomers uncover hidden patterns and make groundbreaking discoveries that were once thought impossible. One of the biggest challenges in studying gravitational lensing is the sheer volume of data. Telescopes like Hubble and the upcoming James Webb Space Telescope capture millions of images, each containing subtle distortions caused by gravitational lensing. Manually analyzing these distortions would take an impractical amount of time. This is where AI steps in. By training algorithms to recognize and interpret these distortions, scientists can quickly identify lensing events and extract valuable information about the objects involved. For example, AI has been used to detect faint lensed galaxies that would have otherwise gone unnoticed. These galaxies, often located billions of light years away, provide crucial insights into the early universe. By analyzing their light, AI helps astronomers determine the distribution of dark matter and the rate of the universe's expansion. This not only enhances our understanding of the cosmos, but also opens up new avenues for research. Another exciting application of AI is in simulating gravitational lensing events. Supercomputers combined with AI can create highly detailed models of how light bends around massive objects like galaxy clusters or black holes. These simulations allow scientists to test theories and predict how lensing will behave in different scenarios. By comparing these predictions with real observations, researchers can refine their understanding of gravity, dark matter, and the structure of the universe. AI is also playing a key role in identifying rare and extreme lensing events. For instance, it has helped discover multiple images of the same distant object created by the gravitational pull of a massive foreground galaxy. These events, known as strong lensing, provide a unique opportunity to study the properties of both the lensing object and the background source. AI's ability to sift through data and spot these rare occurrences is revolutionizing our ability to study the universe's most extreme phenomena. As we continue to push the boundaries of technology, the partnership between AI and gravitational lensing promises to unlock even more secrets of the cosmos. From mapping dark matter to discovering distant galaxies, AI is proving to be an invaluable ally in our quest to understand the universe. Next, we'll explore the future of gravitational lensing research and the exciting possibilities that lie ahead. As we look ahead, the future of gravitational lensing research is brimming with potential, promising to unlock even more secrets of the cosmos. One of the most exciting prospects is the discovery of new exoplanets. Gravitational microlensing, which magnifies the light of distant stars, has already revealed planets that are too faint or far away to be detected by other methods. With advancements in technology, we can expect to find even more of these hidden worlds, some of which might harbor conditions suitable for life. This could bring us closer to answering one of humanity's most profound questions: are we alone in the universe? Another frontier lies in the study of dark matter and dark energy, two of the greatest mysteries in modern astrophysics. Gravitational lensing provides a unique way to map the distribution of dark matter, as its gravitational pull bends the light from distant objects. Future telescopes like the Vera-C Rubin Observatory will capture even more detailed images of lensing events, allowing scientists to create precise maps of dark matter across the universe. These maps could reveal how dark matter shapes galaxies and galaxy clusters, shedding light on its true nature. Dark energy, the mysterious force driving the accelerated expansion of the universe, is another area where gravitational lensing will play a crucial role. By observing how lensing distorts the light from supernova and other distant objects, researchers can measure the rate of the universe's expansion with unprecedented accuracy. This could help us understand whether dark energy's influence is constant or changing over time, offering clues about the ultimate fate of the cosmos. The next generation of space telescopes, such as the James Webb Space Telescope and the Nancy Grace Roman Space Telescope, will take gravitational lensing research to new heights. These instruments will peer deeper into the universe than ever before, capturing images of galaxies formed just after the Big Bang. By studying these ancient objects through the lensing effect, we can gain insights into the early universe and how it evolved into the cosmos we see today. Artificial intelligence will continue to be a game-changer in this field, helping astronomers analyze the vast amounts of data generated by these advanced telescopes. AI's ability to identify subtle patterns and anomalies will accelerate discoveries, from rare lensing events to new types of cosmic phenomena. Together, technology and human ingenuity will push the boundaries of what we know about the universe. The possibilities are endless, and the discoveries waiting to be made could reshape our understanding of space, time, and reality itself. Gravitational lensing is not just a tool for observing the universe, it's a window into its deepest mysteries, and the future of this research is as vast and exciting as the cosmos it seeks to explore. As we wrap up our journey through the universe's most extreme gravitational lensing events, it's clear just how much this phenomenon has transformed our understanding of the cosmos. From bending light around massive objects like black holes and galaxy clusters to revealing the hidden presence of dark matter and dark energy, gravitational lensing has proven to be one of the most powerful tools in astronomy. It has allowed us to peer deeper into space than ever before, uncovering ancient galaxies, distant supernova, and even rogue planets wandering through the void. Each of these discoveries has brought us closer to answering some of the biggest questions about the universe, its origins, its structure, and its ultimate fate. But the story of gravitational lensing is far from over. With cutting-edge telescopes like the James Webb Space Telescope and the Vera-C Rubin Observatory on the horizon, we're poised to uncover even more secrets. Artificial intelligence is revolutionizing how we analyze data, making it possible to spot rare lensing events and cosmic anomalies that might have gone unnoticed. And as we continue to map the distribution of dark matter and measure the expansion of the universe, gravitational lensing will remain at the forefront of astrophysics, guiding us toward new breakthroughs. So, what's next? The universe is vast and its mysteries are endless. Gravitational lensing has already shown us that the cosmos is far stranger and more wondrous than we ever imagined. But there's still so much to explore. What other hidden worlds might be out there waiting to be discovered? Could gravitational lensing one day help us find evidence of life beyond Earth? Or perhaps even reveal clues about the existence of parallel universes. The possibilities are as limitless as the universe itself. If you've enjoyed this deep dive into the wonders of gravitational lensing, don't stop here. Hit that like button, subscribe to the channel, and ring the notification bell so you never miss out on our next cosmic adventure. And let us know in the comments what fascinates you most about gravitational lensing. Is it the mind-bending science, the stunning images, or the potential to unlock the universe's greatest secrets? Whatever it is, keep exploring, keep questioning, and keep looking up. The universe is waiting to reveal its next big